Hello, this is Mahsa Shirazi and welcome to Math Inside Studio. In this video, we are going to learn about Gauss-Jordan method and we will see the difference between Gauss-Jordan method and Gaussian elimination. And we will solve one example together. Suppose that you have this linear system, 4 equations and 4 unknowns. And if you want to use Gaussian elimination or Gauss-Jordan method, the very first thing is to form the augmented matrix. For this case, the augmented matrix looks like this. I'm going to explain in more details how you'll get this augmented matrix later on in this video when we're going to solve this problem. But for now, just consider this as the augmented matrix. Now, if you want to use Gaussian elimination, you are using elementary row operations to follow 3 main rules to make a matrix look like this. So this is in row echelon form or REF, okay? And the 3 rules are these ones. So the very first thing is that if you get any 0 row in the process of reducing the matrix, you should put the 0 row at the bottom using interchanging, okay? Now consider the leading ones, the ones that I circled around. So here, the rule number 2 says that we want all entries below a leading one to be 0. All right. And the third rule says that if you consider any leading entry, any leading one, you want this leading one to be to the right of the ones in the above rows. Okay. Now, if you follow these 3 rules, this is basically Gaussian elimination. And for Gauss-Jordan elimination, we have one extra step, okay? So not only you want the entries below the leading ones to be 0, you want also the ones above the leading ones to be 0 as well. So if you follow these 4 rules using elementary row operations, you form reduced row echelon form, and when you have this form, you can convert everything back into equations, okay? And you will see that this system is much easier to deal with this system, the original system. All right, let's consider this linear system. So the very first step is to form the augmented matrix, right? So if you remember, in the augmented matrix, the rows correspond to equations and columns correspond to variables, right? For example, if I want to write down the first row, I look at the coefficient of x1, which is 1. I put 1 here. The coefficient of x2 is -1. I put -1. Coefficient of x3 is 2, and x4 is 1. And then I put the constant term, okay? So this line is not mandatory to draw, so it somehow separates the coefficients and the constant term, but it's up to you. You can put it or not, okay? So similarly, we form row 2. So the coefficient of x1 in row 2 is 0. So this is basically right like 0x1. So it's going to be 0, -3, -3, and again 0, right? And then the constant term. Now for row 3, it's going to be 0, right? 2, 2, 1, 8. And the last row is going to be -3, 3, -6, -3, and -9. So this is our augmented matrix. So now I need to pick the leading entries, okay? So how we do that, we start from the upper left and we move to the lower right, okay? So the leading entry of the first row is going to be 1. I pick that. If it's something other than 1, then we have to scale it, but here we don't need it, right? And I'm going to use that. I'm going to use that leading one to make everything under it to be 0. So in this case, these two are already 0. So I'm going to use this to make this to be 0. And to do that, I use replacement. So I'm going to replace row 4, the last row, by row 4 plus some coefficient times row 1. I'm going to use row 1, right? So what should that be? -3 plus 3 times 1 makes it 0. So it should be plus 3 row 1. And this is the new matrix we get. I'm going to quickly rewrite everything, like the very first 3 rows. We're not changing them in this step. Now, let's do the calculation here. So -3 plus 3 times 1 gives us 0. 3 plus 3 times -1, 0. -6 plus 3 times 2. -3 plus 3 times 1. -9 plus 3 times 3, which is again 0. So we got a 0 row, right? If you got this 0 row like in somewhere else, you had to first bring it down. But here it's like the very last row. So this was one of the rules, right? So we keep it as it is. Okay. So we are good with the first leading one or first pivot, right? Let's move to the next row. In row 2, -3 is gonna be the leading entry, and we first need to scale that, right? To make it as 1. So row 2, I scale it by 1 over -3 times row 2. Okay, so I'm quickly gonna write down the first row. We're not changing it right now. And then divide everything in row 2 by -3. So I get 0, 1, 1, 0, 2. And I'm going to rewrite the other rows. Okay, so now this is the leading one or the pivot of the second row. And I'm going to use it to make everything under it to be 0, right? So this is the only non-zero term. So what I'm going to do is I'm going to use replacement. So I'm going to replace row 3 with row 3 plus -2 times row 2, right? Or you can just write it R3 minus 2R2, okay? And what I'm going to get is I'm going to just quickly write down the first 2 rows. And then I have 2 minus 2 times 1, 2 minus 2 times 1, and then 1 minus 2 times 0. And the last one, 8 minus 2 times 2, which is going to be 4. And there we go. This is going to be the second leading one or the second pivot, and everything under it is 0. So we are good with that. Let's move on to the next row, row 3. Choose the pivot. It's already 1. I don't need to scale it. And look at that. Everything under it is 0. Okay? So far, we have all the leading ones. Everything under them are 0. And we have this staircase form. And we know that this form is actually the row echelon form, right? If you wanted to solve this question using Gaussian elimination, you had to stop here and then use back substitution to solve the problem. But for Gauss-Jordan, we need to do one more step, right? So look at the columns in which you have the pivots. So this is the first column, the second column, and the fourth column. Okay. The additional rule for Gauss-Jordan method is that we want everything also above the leading ones to be 0, right? So everything under them is already 0. We want to make everything above them to be 0 as well. So I'm going to start with the very last column. Okay. And I'm going to use this row to make this one to be 0. So I need to do the replacement. So I'm going to replace, I want to change this, right? So I'm going to replace row 1 with row 1 minus row 3, right? So if I say 1 minus 1, I get 0. This is exactly what I want, right? So let's do this calculation. So 1 minus 0 is 1, negative 1 minus 0, negative 1, 2 minus 0, 0, 2, sorry. 1 minus 1, 0. And then at the end, 3 minus 4 is going to be negative 1, right? Okay. So I'm going to quickly rewrite everything else. And now look at this column. Look at fourth column. Everything above and under the leading one is 0. Okay. Now let's look back here. I move to the second column. The column has the leading entry, right? And my goal is to make everything above it to be 0, right? So we are done with this one. We are good with this one. This was another leading entry. I'm going to focus on that, okay? I'm going to use this column. And I'm going to use this to make everything above to be 0. So again, I'm going to use replacement. So replace, you want to change this. So I need to replace row 1 with row 1 plus row 2, right? If I add this and this, I make this one to be 0, right? So it's going to look like this. 1 plus 0, 1. Negative 1 plus 1, 0. 2 plus 1, 3. 0 plus 0, 0. Negative 1 plus 2 is going to be 1. I'm going to quickly write down everything else. And now, look at this one. Everything above and below the leading entry is 0. So I move to the next column, including a leading one, which is going to be the first column. Look at this one. In this one, obviously, there is nothing above, so we are done. Okay. Now look at the form now. This is the staircase form. We have the leading ones, everything below and above them are 0. So this form is the reduced row echelon form, or RREF. Okay, and we are going to use this matrix to solve the problem. Okay, so in this step, I have to figure out which variables are leading variables and which one are free variables, right? So I know that this corresponds to x1, this corresponds to x2, x3, and x4. And the columns in which you have the leading ones are going to give you the leading entries, right? So here, leading entries are x1, x2, and x4. And the free variables Sorry, let me write it down. Leading variables are the ones that are not leading variables. So here only x3 is going to be the free variable. Okay, so we know that we have to write the free variables as parameters, right? So set x3 to be some parameter, let's say t, and t can be any real number. Okay, and I'm going to use back substitution to solve this system. So this is equation 1, this is equation 2, equation 3, and equation 4 is basically 0, 0, 0, 0. I don't care. So I start from equation 3. So this tells me 1 times x4 is equal to 4. So from equation 3, what do I get? I get x4 is equal to, sorry, x4 is equal to 4. Okay. Now, move to the next equation. So equation 2, it says 1x2 plus 1x3 is equal to 2. So from equation 2, I get x2 plus x3 is equal to 2. But I know that x3 here is the free variable, so I can replace it with t. So what I get here is x2 plus t is equal to 2, which means that x2 is equal to 2 minus t. And from the first equation, from equation 1, I get x1 plus 3x3 is equal to 1. And again, I have to replace the free variables with the parameters. So I get x1 plus 3t equal to 1, which means that x1 is equal to 1 minus 3t. There we go. We have all the variables, and we can form the general solution now. Okay, so the general solution is going to be all vectors in which x1 is going to be 1 minus 3t, x2 is 2 minus t, x3, we set it to be t, and x4 to be 4. And t can be any real number. And there we go. All right, that's how we solve this problem. Thank you for staying with me and solving this problem together.